The Sargasso Sea off the coast of Bermuda. Marine biologist Dr. Anne Cohen is studying how the moon affects the growth of corals. She's looking for a species known as Diproria strigosa, the brain coral. Every 29 days, on a full moon, brain corals grow a new layer of skeleton on top of the old. This growth spurt is dictated by the monthly orbit of the moon. It's like clockwork. And the skeletal layers can be used as a lunar calendar, a record of time passing.
So this is the coral that we pulled out of the water today. And if we look under the microscope, you can see very fine ridges. And we know that these are formed on the lunar cycle. These are monthly bands.
Okay, so it's a bit like the rings of a tree. You can use that to date it.
That's right. And actually, we can count about 65 monthly bands
Oh, right, yes.
in this coral, which makes it just over 5 years old.
That's pretty amazing.
But some corals are even more revealing. They allow us to peer into the distant past and find out something extraordinary about the power of the moon. This is a fossil coral from the Devonian era. It's 400 million years old, but still beautifully preserved. As well as monthly growth bands, there are annual bands, and even daily bands, 1/4 millimeter apart.
So this coral grew about 1/4 millimeter every day.
That's right.
400 million years ago.
400 million years ago. And if we took the time to count up all these daily growth bands within the year, we'd find not 365 days, but in fact in this coral there are 400 bands every year. 400 days a year.
400 bands.
Per year.
So that means that there was an extra 35 days every year.
That's right.
That's quite mind-boggling.
If there were really 400 days in the year back then, how long was each day?
If you do the sums and take the total number of hours in a year and divide by 400 days, then you come to the conclusion that in the Devonian period, when this fossil was alive, a day actually lasted 21 hours and 55 minutes. Now, I must admit, I find that really weird. The fact that in the past, a day wasn't 24 hours.
The length of a day is simply the time it takes for the Earth to spin once and go from one sunrise to the next. If, in the past, days were shorter, then the Earth must have been spinning faster. In fact, back in time, back billions of years, the planet was spinning so fast that each day lasted just 5 hours. But why should the spin of the Earth have changed over time? Because of the moon.
When the moon formed, it was so close to the Earth and pulling so hard that it acted as a brake on our planet. By chance, the Earth was spinning this way and the moon was pulling that way. The net effect was that the Earth slowed down.
For billions of years, the gravitational pull of the moon has been putting a brake on the spin of the Earth, and days have been getting longer. What was once 5 hours now lasts 24.
We humans have been around for such a short time, about 200,000 years, that we've only ever known 24-hour days. Our body clocks are completely geared for that length of day. And yet we only have 24-hour days because of the moon.
It's amazing to think that the very rhythms of our planet have been set by this ball of rock out in space. But what about the moon itself? How has it been affected by the spin of the Earth? Well, one of the first things you learn in physics is that for every action, there is an equal and opposite reaction.
As the Earth has been slowing down all these years, something else has been speeding up. And that something is the moon. For billions of years, it's been getting faster. And what happens to something in orbit as it gets faster? Well, imagine the centre of this roundabout is the Earth, and I'm the moon in orbit. As we speed up, I get slung outwards, and I feel as if my body wants to move into a wider orbit. And that, more or less, is what's been happening to the moon.
As it's been speeding up, it's also been spiralling outwards into a wider and wider orbit. But is it still spiralling away? Or has it stopped? There's one way to find out. Apache Point Observatory in New Mexico. One of America's largest telescopes. It's also one of the last outposts of the Apollo program. Besides having a lot of fun on the moon, the Apollo astronauts were running a series of scientific experiments.
Roger, David, looks good to us. Handle down.
And on 3 of the missions, they left behind retro-reflector units, packed with small mirrors. This one is from Apollo 15. And ever since, astronomers have been firing lasers at them to keep track of exactly how far away the moon is.
So once we're all centered up on Apollo 15, I can open the shutter and we're ready to shine the laser.
Dr. Russet Macmillan carries out the laser ranging at Apache Point.
So you're now sending pulses of laser light out towards the moon?
That's right. They're going to travel to the moon, get reflected, come back, and get detected by our detector.
So how much of the light do we actually get back?
Well, we're sending out about 100 quadrillion photons with each pulse. If we're lucky, for each pulse, we might get back 1 photon.
1 photon back?
1 photon out of 100 quadrillion going out.
A photon is a tiny particle of light, and 100 quadrillion is a phenomenally large number. But by capturing just a few photons, it's possible to measure the distance between the Earth and the Moon, down to the last millimetre.
As of right now, the distance to the Moon is 393,499 kilometers, 257 meters, and 798 millimeters precisely.
Astronomers have been using lasers to measure the Moon's distance for nearly 40 years now. And what they're finding amongst all those photons is a very clear pattern. The Moon, which has been drifting away from us for billions of years, is still drifting at a speed of 3.78 centimetres a year. In human terms, that's about the same speed that our fingernails grow.
Does it matter that the Moon is drifting away from us? Well, for one thing, if it keeps going, we'll lose a great natural wonder.